Good day everyone. Today I'm going to share with you about one type of cement, which is a blended cement. Blended cement can be defined as uniform mix of ordinary Portland cement, OPC, and blended material such as silica fume, fly ash, limestone, and slag to enhance its properties for different use. Blended cement is a combination of Portland cement, water, and blended material. There are 4 types of blended cement. First is type IS or Portland slag cement. This type of cement containing 70% of slag and generally used in construction. The second one is type IP, which is Portland pozzolan cement. This type of cement contains 50% of pozzolan, which are fly ash. The third one is type IL, which is Portland limestone cement. This type of cement contains 5 to 50% of limestone in the ground. Finally is IT, which is ternary blended cement. This type of cement is a combination of 2 types of blended materials such as silica fume, fly ash, and slag. Seawater is a harsh environment in which concrete infrastructure such as seawalls, jetties, and water tanks deteriorate rapidly. Corrosion of steel reinforcement or disintegration of concrete is a sign of concrete structure deterioration. Corrosion of steel reinforcement is a major cause of RC structure failure in marine environment. Water and salt iron pass through the concrete cover and make contact with the internal reinforcement. The rebar oxidize and corrode as the result of this process. The most common cause of concrete deterioration is chloride-induced reinforcement corrosion. Rust takes up volume and causes tensile stress in the concrete, which eventually lead to spalling and cracking. The problem statement of this study is to determine the performance of blended cement concrete when exposed to marine environment such as marine reinforced structure.
Basic concept. Portland cement with additional finely split particles in various but well-defined quantities is known as blended cement. Blended cements made from industrial and agricultural waste have lately gained popularity for their increased long-term strength and durability. Fly ash, powder granulated blast furnace slags, rice husk ash, palm oil fuel ash, calcined clay, and other blending agents are used. It is said to increase rheology and cohesion as well as reduce heat of hydration, permeability, and chemical resistance. Each of these blending material has various characteristics and respond differently in the presence of water. They all have limits and some have conflicting effect on concrete and mortar qualities. The performance of concrete in maritime construction is influenced by a complex interaction of physical and chemical elements. The present specification of Australian standard AS3605 are suitable for ensuring durable concrete for stipulated design life of 40 to 60 years. When the structural member is subjected to tidal and splash zone condition, this standard prescribes a minimum typical compressive strength of 50 MPa. Water absorptivity has been specified as a criterion for concrete in marine application in conjunction with prescriptive requirement for minimum binder content, maximum binder water binder ratio, and binder type by certain public authorities in Australia who require longer structural design life of over 100 years. In marine environments, high humidity, sulfate attack, and chloride ion concentration and air lead to much more severe corrosion to offshore structures than structures in inland areas. The cementitious concrete and reinforced concrete structures used in marine projects usually need to be added by some supplementary materials to improve its performance. This is the durability deterioration of concrete under marine environment.
For our case study, the blended cement concrete was exposed to marine environment. There are 2 properties in blended cement concrete. The first one is high permeability and the second one is high compressive strength. For the properties of high permeability, the previous study from Hart et al. Revealed that the addition of fly ash up to 30% replacement level of concrete improve the permeability characteristics of concrete. Thus, it reduces the corrosion time and decrease the corrosion rate of the concrete. For the second properties of blended cement concrete is high in compressive strength. So from the previous study of Kayali and Ju, the using of silica fumes and fly ash with a very high compressive strength of 70 megapascal proof to retain extremely low concentration of fluoride ions. And the addition of silica fume and fly ash significantly reduced the diffusivity of chloride ions in concrete. So the chloride-induced corrosion of steel is unlikely to occur. For design and procedures, there are 9 different mixed designs that are used in this study, as you can see from the table. The water to cement ratio was kept fixed as 0.4. Then, the optimum 4% dosage of calcium nitrate was added into the mixed design. According to the previous case study, there are 4 tests in this design procedure. The first one is compression and flexural test. The second one is chloride penetration test. The third one is the absorption capacity test. And the fourth one is corrosion rate test.
So the next part is data analysis and result. The performance of different mix designs was determined by using several performance related to the tests available. There are compressive and flexural strength, chloride penetration test, absorption capacity test, and corrosion rate test. From that, it can show the result when using cement blended with pozzolanic material in enhanced performance of the concrete exposed to the marine environment. In compressive strength, the target agreement strength of mix design was 5000 psi. From the graph, it shows that all mix designs are achieved except for the mix design of E, F, and G. Next, for the flexural strength, it is similar to compressive strength as shown in the figure, with mix design D is the most highest value. Next is chloride penetration test. The test was performed for chloride ion diffusion coefficient for non-steady state migration coefficient according to the specification provided by NT-Book 492. The average temperature of the analyte solution was 30 Celsius throughout the test, and 60 volts current was supplied for 18 hours. This is the equation. For U is the absolute value of the applied voltage, T average value of the initial and final temperature in the analyte solution, L for thickness of the specimen, X D is the average value of the penetration depth, and D is the test duration. From the graph, it shows that the slag cement in the mix G and T show a lower value of diffusion coefficient than mix content of OPC denoted as A, H, and I. Next is the absorption capacity test. From the figure, it shows that mix design E is the higher water absorption compared to the other mixes. And lastly, the corrosion rate test. It is clearly visible that the corrosion potential that represents the corrosion activity in specimen decrease adequately with the use of the pozzolan.
Assalamualaikum, my name is Raja Muhammad Amir Hamzah. I will give an explanation about discussion. First of all, for compressive and flexural strength, the targeted ultimate compressive strength for the mix design was 5000 psi, and it was achieved by the most of the mix design except mix design E, F, and G. And then all the mineral additive added advantage in the strength except for fly ash. And lastly, all the samples showed reduction in compressive strength after exposure of 100 days to marine environment. Next, for chloride penetration RMT, diffusion coefficient of the same mix design and did not differ by a wide scale in a way justified the authenticity and reliability of the results. Other than that, for absorption capacity test, the minor percentage replacement of cement silica fume proven to be an efficient technique of lowering absorptivity about 8% to 10%. Slag, useful when it substitutes cement in large amounts, also demonstrated a significant reduction in absorptivity. Corrosion rate test. The corrosion inhibitor calcium nitrate was utilized and it greatly slowed down the corrosion process. In concrete samples containing calcium nitrate, there was a substantial amount of models corrosion activity. The graph demonstrates the importance of corrosion inhibitors as well as their future potential. In conclusion, performance of all the mix design in terms of strength gain was better or comparable to the control mix design, except for mix design E, F, and G, where fly ash was used separately or with silica fume and slag. The mix design G showed the best resistance to chloride migration, followed by D and F, demonstrating that slag alone or in conjunction with silica fume and fly ash may make thick, impermeable, and durable concrete. The mix design B and D had the lowest absorption capacity, followed by C and G, indicating that slag and silica fume performed better. In half-cell corrosion rate measurements, the performance of mix design I using calcium nitrate as a corrosion inhibitor was the best, followed by mix design C, F, H, and G. Fly ash performance was once again inferior to the of mix design containing slag and silica fume.